Welcome at our last presentation today. Our speaker is Daniel Kozar. He is a graduate of computer science at the Wrocław University of Technology. Also, he gained experience at a number of different workplaces, most notably while developing set-top box software at Samsung Electronics and EDA solutions at Mentor Graphics. He is currently employed at PSI Poland, where he develops software for networking hardware industry automation solutions. He also describes himself as a software developer struggling for correctness in many possible ways, despite experiencing various obstacles which are a reality of the industry that we work in. Also a big fan of music, the Rocky Horror Picture Show, and looking at his compilers assembly output. So please welcome Daniel Kozar.
Thank you very much, Julia. So welcome, and I'm very glad that you decided to come in such great numbers. The topic of today's talk is Character Encodings Hate Us All. And most of you already probably intuitively know what a character encoding is. However, there is a big deal of misinformation or incomplete information that I have found myself while researching the topic. And I would like everybody to have some ground-level knowledge about character encodings and how it relates to the code that we write. But firstly, as you probably know, or if you have noticed or not, this is my first talk at a Code Dive ever, so I wanted to do everything as right as possible. So I'll be struggling to do this right, so you like the presentation. So firstly, the agenda. And we're going to start with defining what the encoding actually is and what's the difference between binary and text data, because they are both very, very closely related. And then we will look at some programming and the undesired patterns that occur in programming languages, environments, or libraries. Then we'll have a look at some mistakes, and mistakes which were actually caused by mishandling character encoding issues in real-life software, in real-life situations. And then the ending, some good words, since this is the last presentation. So I told you that I wanted to do everything correctly. And in order to do that, I watched some presentations by much more experienced presenters, most notably Andrei Alexandrescu. And he, at a conference at CPPCon, I think it was 2016, he said that in order to make the audience like your presentation, you have to rope them into it. You have to tell them a story. You have to sell them something. So I thought I might as well do that, since there is a story behind this presentation and why I got into the topic in the first place. And it starts like this. Like some would say, as most bad things in life, it starts with Perl. But I'm not one of those people. I'm one of those people who still like Perl very much. And I don't know how much Perl you know, but this is a program which is meant to take one release from the Discogs API and give us the number of the track, which is read via stdin. Sounds simple enough. As you might know, or you don't actually, you shouldn't know that, I'm a collector of CDs, and most people probably still remember when music came to people on these round discs, which were silver at the bottom, because this is actually not that used anymore, so I understand that people might not be familiar with this. But I like to collect them, and Discogs is the site which, for people like me, it enables them to tick, I have this release of this CD, and this is all great fun. Actually, this is actually a minimal example, because the real script behind this was much more complex. We'll get to that in a second. But first, let's check how this works, shall we? So the release, the link that you see on the right side of the screen, this is a release by a Polish group called Manem, and this is the album called Nocny Patrol. Are there any Manem fans in the audience? Okay, so can you give me a track from Nocny Patrol? You cannot, and that's all right. Okay, so as I said, the script gets the track number via stdin, so we will echo explosia. And we'll see what's the number of the track. And it's track number 6. This is a great success. But the album also contains the track called Miłość jest jak opium. And it doesn't work. So, and why it doesn't work, I hope that I will be actually able to explain during this very presentation. Yeah, so I had the problem with my Perl script. So I went to get some help. So where did I go? What's the first place that you go to if you have problems with software or with programming more specifically? Of course, Freenode. Yeah, that's great. Yeah, Freenode. So I went to Freenode, and I went to the Perl IRC channel actually, and I asked the people there this: what am I doing wrong? Very generally speaking. And this is the very short description of what the script was actually doing down there. It had to look up a name from the file system and cross-reference the release with a folder name because reasons. Yeah. So this one, just another Perl hacker, told me that all bets are off. You should just quit programming right now. So I said, what do you mean? Is the problem with me? No. It's character encodings and they hate us all. So when I saw this, I realized that I stepped into something that is much, much bigger than me. And of course, the person then proceeded to tell me how I should handle this issue in Perl in order to actually make it work and make it right. But I remembered this as a cornerstone, actually, of all the issues that can occur when handling characters. And I decided to make a presentation about it because I figured that some people may also be in a similar situation to mine. The general gist of everything is this: bytes are meaningless. You cannot reliably assume that all the bytes that your program receives through some kind of an input-output system can be interpreted as characters. And the people here who do lower level programming, I'm sure are very, very well aware that if you are so inclined, you can simply read a floating point variable as text. You can pretend that it's text. Of course, the result will be garbage, but you can still pretend that it's text because this is just an issue of giving those bytes a meaning. If your program gives some bytes the wrong meaning, the result will be garbage. And in order to protect, to battle, to combat these problems, we use types in higher level languages. So we have a type for int, we have a type for float, we have a type for double. We have types for higher level structures that actually reflect the business logic of our program or some management structures or anything. We have types which are useful to our program. But in case of text, in case of strings, the issue is much more complicated, and this is where character encodings come in. Because what constitutes a string? What kind of properties do bytes have that enable us to call these bytes text, to call these bytes a string? Keep in mind that I'm not talking about the implementation of a string here. For the reasons of this talk, a string could just as well be a sequence of characters. If you were so inclined, you could just as well store these characters in a linked list. It wouldn't make any sense probably, but you could do that. For the reasons of this talk, we're not going to talk about small string optimization, about capacities, about pointers, about memory allocation. No, this is just implementation details for the purposes of this presentation. And what kind of data does it carry? Like I said, we have to ask ourselves, what kind of properties do these byte streams have that enable us to call these byte streams some text? Is there some implicit information encoded inside the byte stream, or do we need or does the program need actually, some explicit information to interpret those bytes in a certain way? And lastly, what makes text distinct from binary data? Because this is a very, very important distinction which is lost at various levels. So let's take a story of a string, or what we call a string. So we have a language. This actual snippet is C++, but this could really be any language which supports the auto keyword and string literals. Let's assume this is C++, and depending on the settings of the compiler, depending on the settings of the runtime environment, or in some very weird cases, depending on the settings of the operating system of the build machine, the compiler is allowed to output any of these byte streams. And they all represent that very string that we saw on the last slide. So the problem is, when we want to convert these byte streams back into our string. Okay, so let's assume that we take the last byte stream because it's pretty and it's pink, and we write another program which receives this very byte stream as input. This is again C++. You could probably use std_byte in place of this. So yeah, this is the input of our second program, which wants to interpret these contents as a string and preferably get the same string back. But again, depending on the settings of the runtime of the compiler that was used to compile the program which reads this string, this byte stream, and again, in some very deprecated cases, settings of the operating system on which this program runs, we can get any of these results. This is horrible. I mean, look at this. It doesn't even look like text. And most specifically, it doesn't look anything like our original string. If we wanted to actually call a comparison or anything like that, in some of these cases, it's not going to be possible, and most importantly, it's going to return false. But how can it return false when the byte stream was actually serialized and deserialized according to the default settings, or the settings that are usually employed by the software or the runtime? There is one, the worst case scenario actually is the green one, because some environments think they are being helpful by skipping some bytes or some characters in this case altogether, or replacing them with placeholders which give us no real meaning at all. So this is even worse, and this is why it's important to be explicit, but we'll take a look at that in a moment. The question that I want to ask once again is why is that? Where do all these issues come from? If you were paying attention, there was in the IRC conversation, I used the term called ASCII range, and you also probably already know what ASCII is, and I don't need to explain it to you. But what was the reason behind ASCII? And the reason actually goes way back. I'm not sure if this is even if you can see this chart correctly. But what it is a scan from a publication called A Survey of Coded Character Representation. This is the table as it existed back in 1960. So back in 1960, you had a lot of different computers, a lot of different operating environments. And those computers were not interconnected. So usually this was not an issue. Because if you somehow wanted to, let's say, send a E this is a Bendix typewriter, and we want to send an E, and this E uses the value 6 to be represented. Oh no, it's actually 5. And if we wanted to send this E to, let's say, this Lincoln Rider machine, we get garbage. This is not the worst issue that existed back then, because like I said, computers were not interconnected, and it was actually very rare, and I don't even know if it was physically possible to get a byte stream, or back then these weren't actually bytes, because as you can see, these are all 6-bit values. Because back then, it wasn't actually that common to get data from one computer to another. But what I want to call your attention to is the fact that all these character sets on these different machines, they all use slightly different sets of characters. It is possible that if you were to get the character E on one machine, it is possible that the second machine doesn't even know what a character E is. It doesn't support drawing it. And this was the issue that came up back in 1960, because this paper is from 1960. It even says 9th October of 1960 at the bottom. And this guy, actually, Robert William Bemer, he was one of the people behind ASCII. And it was the 60s. Computers became much more interconnected, and the need for a universal character encoding finally appeared, because you wanted to be able to say, I have an E on this machine, and I want that second machine to even draw me an E. Is it so much to ask? Yeah, so ASCII was a solution to this problem. This is the original ASCII chart from one of the first standards as published. It's not from the actual first standard, because in the first standard there were no lowercase letters, and I think it was published in 1962 or 63. And whole this block here, it was left as unassigned, as reserved. And the issue one after that, it defined this range as lowercase characters. What is characteristic of this very chart? We can see that, first thing, it uses 7 bits. ASCII is always 7 bits, no matter what anyone tells you. Standard ASCII is always 7 bits. There is no such thing as extended ASCII. ASCII is always 7 bits. But I mentioned the term that I don't really like to use, and this is extended ASCII. This was created when problems with standard ASCII became apparent. And as you can see, ASCII itself only defines uppercase English letters, lowercase English letters, some typographical characters, and some math characters. And this was supposed to be enough. But since the publication of ASCII, and so it was published in, say, 1967, I'm not particularly sure about the date, since then, computers have made their way into other countries. So these were the times of the Cold War and the Iron Curtain in Europe. So they mostly made their way back to Western Europe by now. And when the French and the German saw that they cannot have their accents or their umlauts inside their computers, they said, "Oh, incroyable und unglaublich." Of course, there were ways around that. You could write the accents as O and a dash. You could write umlauts as AE or OE or UE, but was it really the way that they should be written in? Is it really the same text that we want to input into the computer? German orthography, of course, allows writing O with O umlaut with as OE, but there were there were problems related to that, mostly for mostly comparison. And all these environments, which were not necessarily English-speaking, they created their own standards, because they looked at this table, and what did they see? They saw, hey, this is just 7 bits. We have 1 extra bit to use. We have 128 more choices to stuff our characters into. And that's where the term extended ASCII comes from. It comes from the fact that you extend the code by 1 bit. However, all these standards are not mutually intelligible. And that's why there is no one extended ASCII standard, and it should not, this term shouldn't ever be used. If you're going to work with legacy encodings, use the name of the encoding. And I mentioned French and German as one of the reasons, as examples of languages which use extra letters which are not present in ASCII. But of course, the same problem actually existed in a lot of different countries. Poland, most notably. All the other Slavic-speaking countries, or rather countries speaking Slavic languages. And the worst case was countries which don't necessarily speak a language that uses the Latin alphabet. So this would be Bulgaria, Serbia, and of course Russia, and all the Western, Eastern, world. Of course, computers made their way through there as well, and they also invented their own schemes for extending ASCII with their own letters. So in Poland, it looked like this. Those first 3, on the left you can see the name of the standard, and on the upper side you can see the letter itself. So in Polish we have 18 extra letters compared to the standard Latin alphabet. And you can see that there is a multitude of standards, all of which employ the extra bit to encode the same letter with a different byte. So this is not good. How can we say that this is character L or this is character Ni if the byte value of this character in every encoding is potentially different? This led to a multitude of errors that I hope I will be able to show you later on. But this is how the issue looked like in Russian. I'm actually quite amazed by this because I found this, I think we can call it a flowchart. This flowchart, actually, I found this while researching the subject. And this is, it says, do the letters look Russian? Do you have the symbol this? Oh, then it's probably UDF-16 converted to CP866. And there are actually sites in the internet which do their best to decode this phenomenon of wrongly encoded text. So this still remains an issue. Yeah. So what was meant to end all these issues? Unicode. Unicode, in the words of its creator, the name was chosen to signify a universal encoding, which can encode all characters and all writing systems in the world. They generally forgot about how mutually contradicting writing systems can be. For example, in most writing systems, you would expect the character's space, not to take up, not to resolve into anything that's visible on the screen or in the text. However, Unicode also encodes a writing system for ancient Irish, which used vertical and horizontal dashes in order to encode letters. And in that very writing system, a space is a horizontal dash, and vertical dashes mean the letters. I mean, the number of dashes then is resolved to somehow decode to a letter in that very language. But it generally worked out very well. I'm sure that right now on your computers, on this computer most probably, and most surely actually, in your phones, you are using Unicode everywhere. But there's also a slight misconception about what Unicode actually is. At its essence, Unicode is just a mapping between a number and a character. It's nothing more. And I would ask you to, during this presentation, to constrain yourself to this definition. If you have more knowledge about Unicode, that's great for you. But please do remember that at its core, Unicode is just a mapping between a number and a character. It just says that we have a character, and it looks something like this. We have a very vague description of it, and it's like this, and we give it a number 20. I think it's space. Yeah, so at its core. It's also a database containing information about each of these characters, and the examples of this information include the uppercase form of the character #S in German. Anyone? I see there are some German speakers in the audience, so this shouldn't be a problem. It's 2 uppercase normal S's. Not anymore. Great. However, the Unicode standard still defines this as 2 uppercase S's, although, as Ulrich rightly noted here, the German Orthography Institute or something said that there is a separate uppercase letter for this. However, Unicode decided not to incorporate this into older versions of the standard because it would cause a great number of problems, most related to sorting. Yeah, so there is also a separate uppercase letter of this character, but it's not the uppercase form of this very character. And this is actually also another example of how mutually contradicting Unicode can be at times. Is this character that you see on the screen, is it a digit? Certainly looks like one, but it's not, because it's the Cyrillic character Z. Also, are the characters, these characters, are they mutually interchangeable? Those are ligatures, so this is a character made out of two letters and they are combined together. They are also not interchangeable despite looking the same, because one of them is Latin and the second one is, I think, Cyrillic or something like that. But just because the character looks the same doesn't mean it's interchangeable or that it's a digit, because it looks this way. And Unicode helps us define all this, and it certainly, firstly, it would cause a lot of work for you to get all this information by yourself, and it would also, and you would also probably be slightly wrong in some cases, like these ones here. It also defines some algorithms for combining and rendering characters. So Unicode has this notion of a combining character that I'm not going to get into because this is not really the point. But in a giant nutshell, it allows some characters to be composed and decomposed. But what it means is beyond the scope of this talk, most generally. And what Unicode is not, it's not a character encoding. Because up until now, we defined character encodings as schemes of mapping characters into bytes. Because all those legacy encodings that I showed you, it showed that there is a mapping between a character and a byte. Unfortunately, this is not true anymore with Unicode, because Unicode defines a mapping between a character and a number. And this number may, and most of the time is, larger than what a byte can hold. It's not necessarily simple to handle properly. Unicode can be very complex. And drawing systems which use Unicode can also be very complex. All this complexity adds up, and then you get text messages on iPhones breaking your phone because it had a very, very weird case of combining characters and modifying characters and left to right switching, and software gets confused because of all this complexity. And most generally, it's not a silver bullet. There is no magic wand that you can just wave over your legacy code base and say, we're using Unicode now. It's not that simple. Every case of porting existing code bases into Unicode requires a review of the kinds of files that the application works with and what the application does with its strings inside it. Okay, so I said that Unicode is a mapping at its core. And this is an example of this mapping. You can see that we have a Latin letter, a Cyrillic letter, a mathematical symbol, and a playing card, because why not? And you can see on the left side of the table, those symbols are drawn as they are represented by the fonts that I used. And in the second column, you have a number. And in most contexts related to text, U plus hex number means Unicode character which has the number, this number in hex. And you can see that there is that the Latin symbol can be encoded using just, actually in this case, it would need 7 bits. It can be encoded using 7 bits. So this is good because this means it's the same value as it had in ASCII. This is great. Next value, the next character, the capital letter, the Cyrillic capital letter Z, has a slightly larger value. The next one has also a larger value, and the last one is also the only one here that wouldn't fit on 16 bits. So you can see what I meant by saying that Unicode defines a mapping between a character and a number. And this number is currently limited to 20 bits, I think, although I'm not sure. Okay, and I also said that Unicode is not a character encoding. It also defines a number of algorithms that turn these numbers that are assigned to characters into the byte stream. And this is an example of mapping that first character, this is the letter A, with different UDFs. So this is a Unicode transformation format. And there are 3 ones, at least those 3 ones are most widely used. We have UDF-8, 16, and 32. 32 is the most simple of all these because it just takes the number assigned to this character and it just puts it in that 32-bit variable and writes it into a byte stream. Very, very simple. UDF-16 does the same thing, but with 16 bits. And can you see any immediate problems with UDF-16 or 32? Endianness, yeah. Another one? In terms of strings and byte streams? Zeros. Size as well, because we also come to the realization that a character is not necessarily 1 byte anymore. And zeros, because remember that if there are embedded zeros in the byte stream, then all the functions which expect proper null-terminated C strings, they don't work because they stop at the first occurrence of a null character, a null byte, which is a null character. Okay, and let's see how those other characters are encoded. You can see that UDF-16 is pretty simple, up until the last one, because then some magic happens. UDF-8, magic happens all the time. And UDF-32 is just boring. It's just very, very simple. I'm not going to go into the detail, because this is also not the point of this talk, but just to say very generally, UDF-16, when converting a number into a byte stream, uses a reserved portion of the Unicode standard of the mapping, which is specifically reserved for UDF-16 in order for it to encode values which are larger than 16 bits. And UDF-8, to put it very simply, encodes the number of bits which are following the first byte, encodes the number of bytes which follow the first byte into the first byte. So we have a byte with the highest bit set, and then a number of bytes which allow us to reconstruct the number. The biggest advantage of UDF-8 is its backwards compatibility with ASCII. but we'll get to that at a later point. Okay, let's get into programming. There is a number of undesired patterns when it comes to programming. First of them is the unspecified source character encoding. And this was evident during the first snippet of code that I showed you. We had a string literal inside the source code, and depending on how source character encoding was defined, it could end up as different serialized forms of this string literal. Just because we see a string foobar, or foobar is an easy case actually, just because I see a string with weird characters in our editor doesn't mean that this string will also appear in the same form in the program's memory. Unless, of course, the source encoding is specified, and then we can say, or the programming environment can guarantee, this very string will appear in its very same form as it appears in the source code. It will appear in the very same form in the program's memory or object code or whatever, depending on the specific usage. Second thing, conflating the definitions of byte type with character type. And this is, I think, the one that a lot of people have problems with. Of course, this all began with C when it called the byte type a char. This is obviously not true anymore, because if you want to work with Unicode, a byte is not a character anymore. But this pattern or this disadvantage still plagues a lot of today's languages. Thirdly, we have automatic conversions between bytes and characters. Some languages or some environments think they are being useful by allowing an automatic conversion according to default encoding between a byte stream, or say a byte type, and the character type. And this conversion can occur without any interaction from the programmer or the runtime environment. Yep. And I mentioned a default encoding or a platform encoding. This is also something that is rather undesired, especially if it cannot be overridden. This makes a lot of, don't get me wrong, this makes a lot of sense when you can assume that your program, or rather the byte streams produced by your program, will only be read by another program which is running on the same platform as the one that your program. This is not a very dumb assumption. It works very well a lot of time, because a lot of the time you can make a kind of an assumption like this. But when this becomes something that you cannot override, you have a problem, because you usually need to hack around this by defining your streams to be binary, even if you wanted them to be text, and then handling the conversions yourself, and it becomes a mess that you don't want to handle. Okay, so let's start with some code. Let's try running this simple Python 2 code. And what happens? We get a very useful error message. Just to make realize what we did, we just wanted a string literal. But this actual Python error message is very helpful, because it tells us, hey, you have something that I don't really understand, and without some extra information, I won't be able to understand this, and visit this webpage for more information. So this is great. So yay, Python. Okay, so let's fix it up. As you can see, we fixed it up quite nicely. And the first thing that you'll notice is the fact that we specifically state the kind of encoding that we use in our source code. And this enables the Python interpreter to guarantee us that all these strings that we have, they will have the very, very same representation that we have in the source code. So let's try running this one. We got a false and a true. What happened here? So in order to illustrate some of the issues that some programming environments have, I prepared very simple programs which try to read a a file which is encoded in a let's say extended ASCII encoding. So this is ISO 8859.2, and we'll try writing some code in different environments in order to read it. So what happened here? Firstly, we have two different string literal variables which are assigned a string literal, and one of them is a standard string, and the second one is a Unicode string. And we just try to open the file, read it, and then we try to compare what we got from the file with a literal. And the result here is false and true. And this is because Python 2 is guilty of one of the things that I mentioned as undesired patterns, because what ends up in this literal is what actually is from the is what actually appears in the source code file. So what we have as literal is actually encoded in UDF-8. However, the literal _u is the Unicode type, and it uses a different form of internal encoding, which enables Python to recognize Unicode properly. So when we compare the first variable that we read from the file with a literal, we get false, because what we read from the file were bytes encoded as 8859.2, and what we have as literal are bytes, and the byte encoded, or rather UDF encoded version of our string literal. And as long as we use this, we're fine. And as long as we use codecs open with explicitly stated encoding, we'll also be fine. Fortunately, Python 3 solved some of these problems. So you can see that running this script gives us something very, very bad. And why is that? Yeah, I only have the right version on the table on the slides. Oh no, it's the wrong one too. Okay. All right. So, what happens when we try to open a file with a non-standard encoding normally? We get this. We get, hey, I can't decode this byte that appears in your file. This is good. This is actually desired, because the alternative to this is silently assuming that everything is fine and ending up with variables full of characters that you didn't want in the first place. This is good. So let's comment out these lines, which are made to actually show you that what Python 3 changed is generally desirable. We get two truths. So in this case, oh, it cut off. Well, that's just the comparison. What we get here, well, generally, the way to handle this in Python 3, the easiest way, I think, is to either open the file in binary mode, which then disables the automatic conversion according to the standard or default encoding, and then decode the data according to a specific character encoding manually, or use codecs open, which is analogous to what we saw in Python 2. The biggest change in Python 3 was the fact that this type, I mean, this is a scripting language, so we shouldn't really talk about types, but let's say that this is of type bytes, what we get from reading a binary file. This is bytes. And in order to convert between a byte variable and a string variable, we need to explicitly state the encoding to use. So this is good. This is another way in which Python actually, I think, leads when it comes to handling Unicode issues. Okay, let's talk about Perl. Perl is always fun. So what do we get when we do this? This is once again a program which does roughly the same thing. It tries to read a file and then compare it to a literal. we get nothing. We get nothing, which means that what we read from the file was not really equal to what we have in our literal. So let's try fixing the code. We have, oh no, this one. What do we gain? We gained some calls to the decode function, because similarly to what Python does, what we get from the function, from Perl functions for reading the file, which is done here, is actually raw bytes as they appear in the file. And although Perl doesn't have a separate type to tell us, hey, these are just raw bytes, don't treat them as strings. Instead, it lets us treat those bytes as strings, which means it's also guilty of one of the issues which plague some programming environments. So in order to convert between a byte representation and a string, we have to call the decode function and state the encoding that the file uses. Or, similarly to what Python does, we can just open a file handle with an explicitly stated encoding. And then we're sure that all the strings that we get from this file will already be in an encoding that Perl treats as strings. So let's try running this one. Nothing. So what? That Perl hacker was right. Character encodings hate us all. So what is wrong in this case? Source encoding. On the second slide, without use UDF-8, Perl could not assume that we're using UDF-8 inside our source code, which is why the literals were not marked as actual strings inside Perl's interpreter memory. Okay, and using and running this example finally gives us the very, very desired decoded and from encoded equal to literal. Okay, let's talk about Java, and you can see that there's lots more code instantly on the screen. This does generally what the other programs have been doing. We declare a string variable and assign a string literal to it, and then try different ways of reading a file. And you can see that there are different approaches. First one is using a file reader directly, and the second one is using a file input stream with an explicitly stated encoding. And then we do roughly the same thing but by reading into a byte array first. So let's try doing this. We have the code, and we have some foobar. And we print the result of, I think it was compare to, which returns an int, and we get a number which is non-zero in 2 cases and a 0 in other 2 cases, which means they're equal. So to put it simply, reading a file without explicitly stating the encoding gives us something weird, something that doesn't compare to what we have in our string variable. I'm not really sure this is good or not, because on one hand, what you get from these classes are strings already, so they shouldn't be marked as strings. And the only way to battle this is to first read into a byte array, because this way you have a clear distinction. What I read from the file are bytes, and what I get after decoding are strings. But what about source encoding? We don't see any explicit markings about the source encoding in this case, and just when you thought that Java could not get any weirder, the Java compiler actually has a switch which tells it to treat the source file as it was encoded in the encoding that you choose. So running this example in this case gives us no good results. So imagine the situation when one disgruntled employee is leaving your company. And there is of course a CI system, and he puts this little switch into the Java C invocation, and all your tests fail, because of course you have tests. And nobody knows what to do, and he walks out of the building, and you can't catch him anymore. Okay, C++ 17. I wanted to show you code, and I failed. Mainly the reason behind this is because C++, as C++ likes to do, it leaves practically all character-related or encoding-related issues as implementation defined. Which means that the language gives you almost none guarantees about source encoding, about decode and encode functions. The only thing that it does is conflating the byte type with the character type, which, as we already said, is not a good thing. Although if you're using 17 or 20, I'm not really sure when it appeared, you can, of course, use std byte instead of std uint 8, which would be preferable because it would be convertible that easily. What the standard defines is the basic source character set, which is a slight subset of ASCII. And it practically says that every implementation is required to support these characters inside their source code. And this also applies to the runtime environment. So as long as you're writing C++ 17, you can be sure that your implementation is able to display these great characters and nothing more. It also says that the set of physical source file characters accepted is implementation defined. So I don't think there is anything left for me to say because the standard did it for me. Unfortunately, there is a talk. There was a talk actually at CPPCon in I think 2016 called Unicode in C++, and it took an hour. So I don't think squeezing C++ into this talk would also be a wise choice. I invite you to have a look and have a listen to that talk if you're interested in handling C++, Unicode issues in C++, because firstly you should, and the second thing is there is a lot of differences. There's a lot of difference between various platforms and various compilers. Okay, let's get to the mistakes. The first mistake is misstating the used or valid encodings. Like I showed you in the introduction, there exists a lot of different standards which can be used to encode various characters. And this is a snippet of a Polish standard for a protocol that's used to communicate inside gas networks. And it says that, generally, text fields are allowed to use ISO 7 without Polish characters or Latin 2. What the hell is Latin 2? I have no idea. So in this case, the only choice that you're left with is guessing. We don't like guessing because guessing is the direct enemy of correctness. But in this case, if you're talking to some different devices, you just have to define by yourself the character set that they're using by analyzing the replies that they give you, because the standard in this case, the protocol specification in this case, is pretty much useless. Second thing, this is a screenshot from my banking system, and as you can see, there are some strange things, because this shouldn't be this thing. This shouldn't be this thing. So what happened here? Legacy encodings were interpreted directly as Unicode code points. So if we have a byte stream, and let's say the value 90 in hex appears, and we say, oh, it has a high bit set, so this means it must be Unicode, so I will treat it as a Unicode encoded character number and insert it to my string. And you get this. So this is just the just to show you that I'm generally not kidding, because the number of this character in Unicode is AF, and this was supposed to be J in the encoding called 8859.2. So we can see the similarity. And same goes for this character, which is B6, and it's also sh in 8859.2. Second thing, intermixing legacy encodings. So there's light over at the Frankenstein's place, and this is a screenshot from another banking system, and this, on the other hand, got this part wrong, because it should be an uppercase L, and this should be an uppercase N. And what happened here? Well, generally, the character that we wanted was L, but what the banking system failed to realize, that it was sent as Mazovia, and gave us a lowercase h, because it decided to interpret those characters as Windows 2050. Okay, unfortunately we're running out of time, so I won't have the chance to explain everything, but this is a screenshot of real life encoding issues coming into place. This is from a TV station in Poznań, and this is a much, much bigger issue. And what happened here was, and once again, Cyrillic-based languages come into place. How I can only explain it as this: somebody in Russia used Windows and saved a file in Notepad, and it contained his or her address, of course, written in Cyrillic. Then this file somehow made its way over to France. And the person in France opened the letter, opened the file, and said, okay, those look like Russian letters. Everything's fine. But the core of this problem lays inside Windows, because Windows still relies, for backwards compatibility with DOS, it relies on the notion of a code page, or a default code page. And this is something that you can change in your regional settings. There is an option that says, in case there is no specified encoding of a text file, use this encoding. And in case of a Russian-based Windows, if it was, of course, a code page that supports Russian, because why not? And in case of a French-based Windows, this was a code page that supports French characters. And we ended up with this. Fortunately, there are people who know their stuff and were kind enough to correct these letters so that the letter can reach its destination. Okay, ending. What have we gained? That character encodings are only relevant while doing I/O. In a perfect world, we would have different types for each string in each encoding, or we would have strings which are so high level that we don't care that a character takes up a number of bits. Any conversions between character encodings should only happen on I/O or API boundaries. And there are certain examples of libraries or environments that got this right. My favorite example is SQLite. It always has two versions of a function that takes text, a UDF-8 one and a UDF-16 little endian one. It never lets you call a text-based function without first thinking, hey, how is my text encoded? And Windows is actually also very good in this case, because all its strings, as long as you're using the wide variants of its API functions, all of its strings are UDF-16LE encoded. And so this is okay, but ideally, a conversion should only take place once or twice. Inside your program, a string should be as abstract as possible, because you don't want to, inside business logic or inside when you're figuring out what's the tax rate for, I don't know, Greece, to figure out, oh yeah, but if this recipient's name has this kind of character, then I should use another rate, and oh yeah, and the string can also be encoded in these 3 different encodings. No, it's not the place for this. Explicitly signaling the used encoding helps combat errors. And this can be done in a number of ways. Firstly, you can use a file format that explicitly states its encoding. Example, XML. XML states that all XML standard documents are encoded using UDF-8. JSON, similarly, also requires documents to be encoded using UDF-8, or in case you don't want that, you can Unicode escape some of the characters which don't show up properly or whatever. It also means that you can simply use an encoding which is detectable by itself, and UDF-8 is one of these encodings. And today, when designing a new system, I don't see a reason why UDF-8 should not be used, and this is the main message that I would like to convey to you. Thank you.